This is the question on your screen, and I shall number it my problem number 1. And the question goes like this. Water flows from an overhead tap of radius 5 centimeter at a speed of 2.5 meter per second and falls freely through a distance of 6.10 meter before hitting and spreading across the level ground. Calculate the average force exerted by the water on the ground. So I think you can visualize the problem here. Here is, suppose, the ground, and at a certain height above the ground we have got an overhead tap from which water is flowing out like this, and eventually it hits the ground and spreads across the ground. So we can make an assumption that on water on hitting the ground, it comes to rest momentarily and then spreads out. Look at the data given. They are all given in 3 significant figures. I have said before that if you can, in doing problems in intermediate steps as well, try to maintain 3 significant figures minimum and always report your answers in as many significant figures as given in the data of the problem. One more thing I said in doing problems, try to write down the units also of the quantities involved, because it will tell you that dimensionally you are going correctly or making some silly mistake in the process. So let's start with this problem. First of all, we must appreciate that the speed of water as it comes out of the mouth of this overhead tap, this is not remaining constant because it's falling freely under gravity, right? So if we could just call the initial velocity was u, then the final velocity of the water at the end of free fall as it hits the ground is somewhat higher because it's accelerating under the force of gravity. Now what is that velocity? For that we have got ready-made equation of kinematics. We remember that in rectilinear motion the final velocity square is given by initial velocity square plus twice into acceleration into the distance traveled. Let me remember the equation in its original form. X minus x0 is standing for, of course, the displacement of the particle, in this case water particles in motion. So you might put the values according to the question. The value of u is given to be 2.50 meter per second, and that is squared, plus twice acceleration. Under the free fall condition, you are aware acceleration is the free fall acceleration, that is g, whose value is 9.80 meter per second square. And here the displacement of the water particles as they come out of the mouth of this overhead tap and hits the ground, the distance through which the water particles fall, that distance is given to be 6.10 meter. So here the displacement of the water particles is 6.10 meter. I have written down the units as well, which I have suggested earlier that you should also try to follow if possible. This you calculate and show that this is coming out to be 126 meter square per second square up to 3 significant figures. And if we square root that, then the speed with which the water particles hit the ground is square rooting this value up to 3 significant figures, is coming out to be 11.2 meter per second. I have always said while I do the problems, you also make calculations yourself and confirm the figures. So the speed with which the water particles hit the ground is found to be 11.2 meter per second, significantly higher than the speed at which it came out of this water tap. That was only 2.5 meter per second. My next work is to find out what is the mass of water that is hitting the ground per second. That is dm dt. This is of course a symbol for the amount of water, the mass of water hitting the ground per second. Now you see that looking at the figure, you can see that as the water comes out, since there is no source or sink in the process, whatever water comes out from the jet per second, that is the same mass of water hitting the ground per second, because in the process of fall there is no loss or gain of water. So we can find out the mass of water hitting the ground. It is equal to the mass of water coming out of the water tap, this overhead tap, per second. They are the same things. And what is that mass per second? For that, I'll introduce a figure here. Look, I'm just showing this portion separately. Here we have to understand that the cross-sectional area, suppose of the tap, because if I could fit this cylindrical body of water at the mouth of this tap, you can see that the cross-sectional area of the cylinder is, suppose we call it A, and that cross-section is the same as the cross-section of the mouth of the tap. Now here, what is the length of water or length of the cylinder of water coming out of the tap per second? Now that has to be equal to U, because this is the length through which the water moves per second at the moment coming out of the tap. So you could say that per second, if you could imagine a cylinder of water is coming out of the tap, in 1 second the cylinder's length is nothing but the distance traveled by water jet per second at the instant of coming out of this tap. So we can imagine that this is a cylinder of water coming out of the tap per second, and the volume of the cylinder, since its length is U, length of the cylinder is U, and the cross-sectional area of the cylinder is capital A, we could say that the volume of this cylinder of water coming out per second from the tap is given by the length of cylinder multiplied by the cross-sectional area. And if you multiply that by the density of water, what you get is the mass of water coming out of the tap per second. I'll repeat this once again. I have just said I have drawn an imaginary cylinder of water whose cross-sectional area just matches the cross-section of this tap. And in 1 second, since the water travels the distance of U, so in 1 second the cylindrical part of water coming out of the tap has got a cross-section of A equal to the cross-section of the tap and a length equal to the velocity in magnitude, of course, of the water coming out of the tap. Hence the volume was U into A, and the mass of water coming out of the tap was found by multiplying the volume of water by the density rho of water. This is dm dt, that is the rate at which the mass of water is coming out of the tap. I said as the water falls, you can imagine now as the cylinder is falling from here, each speed is becoming more and more. As a result, I think you can guess cylinder becomes narrower and narrower. I don't want to delve into it much, but I can say the speed is gaining, but at the same time, the cross-sectional area of the cylinder is becoming less and less, so the mass of water coming out per second remains the same as the mass of water hitting the ground below. So this is also the mass of water hitting the ground per second. Density of water into speed of water initially into the cross-sectional area of the tap from which the water flows. We calculate this by putting values here. Density of water is known to be 10 to the power 3, that is 1000 kg per meter cube. The value of initial velocity of water given in the problem to be 2.50 meter per second, and cross-sectional area, be careful here, they have given the data that overhead tap of radius 5 centimeter radius, that was, so a circular base, circular cross-sectional area is given by pi into r square. So I just write it down. The cross-sectional area is coming out to be pi into radius was 5 into 10 to the power minus 2 meter. I'm converting into SI units always, pi r square, and this I must be keeping in square bracket to mean this is standing for the quantity within square bracket is nothing but the cross-sectional area of the tap, that is same as A here. By calculation, I find this quantity dm dt to be 19.6 kg per second. I shall advise all of you to just confirm this result by calculating yourself. 19.6 kg per second. So you have got already the speed with which the water hits the ground and the amount of water hitting the ground per second, that is dm dt. Now the average force applied by water onto this ground is simply given by the change in momentum of water per second numerically. Numerically, the force given by water onto the ground is equal to the rate of change in momentum of water with time. So you can write down the average force. I'm just talking about the numerical value of the force here. This is given by the mass of water hitting the ground per second dm dt into the speed change. Momentum change means the speed change, and I have said that initial velocity was v, and the moment it hits the ground, the velocity becomes 0. So numerically, the velocity change is coming out to be v minus 0, and this quantity is nothing but the average force applied by water onto the ground. So let's put the values here. This is dm dt has been found to be 19.6 kg per second, and the value of v was 11.2 meter per second. This is the velocity with which the water hits the ground, and finally velocity is becoming 0 after hitting the ground. So change is this much only, and we find the average force by calculation is coming out to be 220 Newton up to 3 significant figures. I'm sure you can confirm the results yourself.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.